Hello, dear students. I welcome you all on behalf of Shri Jayendra Rank Zone classes. In previous lecture of wave optics, we have seen the different theories of light, their limitations, then the wave nature of light, Eugene's principle, the concept of wave fronts, wavelets, and primary and secondary sources and primary and secondary wavefronts. In today's lecture, we are going to study about the phenomena of light reflection, refraction, and the Doppler effect by understanding the wave nature. So first, let us understand the laws of reflection of plane waves using Eugene's principle. First of all, let us note down what are the laws of reflection. Here on the surface, we have incident one light ray at an angle of incidence I, and light is reflected at an angle of reflection R. This dotted line represents the normal. So, the first law states that the angle of incidence is always equal to angle of reflection. And the second law states that the incident ray, reflected ray, and normal at the point of incidence all lie on same plane. And incident and reflected rays lie on opposite sides of normal. So now let us first observe the phenomena of reflection using plane wavefront. Here there is a plane surface xy on which we have incident two parallel light rays which forms a beam. Perpendicular distance between them is AB. At particular instant of time, if we see, first ray will first hit the reflecting surface and then second ray, after some time, second ray will hit the surface. Let's say this point is A dash, and by drawing perpendicular line on second ray, the point is P. Now, we can see that these 2 points are in phase right now. When the point at P reaches to the surface XY, the reflected ray from A dash has reached to this point. Let's say that point is R and this point is B dash. So time taken by light to travel from P to B dash and from A dash to R is same, as they are traveling in same medium. Now, let us draw a normal line from B dash to R. From B dash, again, after hitting the surface XY, light will get reflected. So these two are reflected rays. And they will travel simultaneously from B dash and R point. Let's say perpendicular distance between them is A double dash and B double dash. So here we can write that A dash R is equal to PB dash. That is equal to distance is equals to speed into time. Light is traveling with speed c, and let's say time taken by the light wave to travel from P to B dash is t. Now here let us draw the angle of incidence here. This is angle of incidence I. Now, when A reaches XY at point A dash, B reaches point P. So these 2 points are in phase. A dash and P are in phase. And the light ray B has to travel additional distance PB dash to reach XY. During this time, the ray at A dash is already reflected from XY and reaches to point R. Since the medium remain the same, velocity of wave will remain the same. Thus, it covers equal distance in time interval t. So, we can write A dash R is equals to PB dash is equals to CT. This implies that the distance covered from A dash R is equal to distance covered from P to B dash. Now, since the wavefront is perpendicular to wave normal, angle R should be equal to 90 degree. This is the direction of propagation of light, and this is wave front. They both are always perpendicular, so this angle should be 90 degree. Now here, this A dash R is the reflected ray, so this angle is angle of reflection R. The minimum conditions to get R is angle R should be 90 degree and A dash R should be equal to PB dash. Now consider a wavefront AB advancing obliquely towards plane XY. Hence A dash and B dash are incident rays. Now we know that PB dash and A dash R are same. Now draw a semicircle using point A dash as center and PB dash as radius. We have taken A dash as center and PB dash as radius. We have drawn a semicircle. Draw a tangent to the semicircle at point R. We have drawn the tangent to the semicircle at point R. The reflected rays are A double dash and B double dash. Now let's begin with the proof of Snell's law. We have drawn a semicircle here. Now, we want to prove the Snell's law for triangle A dash R B dash and triangle A dash P B dash. Triangle A dash R B dash and triangle A dash P B dash. We can write A dash B dash is equals to B dash A dash, which is the common side. We already know that PB dash is equal to A dash R, which is equal to CT, and angle A dash R B dash is equal to angle A dash P B dash, which is equal to 90 degree. This line is also 90 degree. So we can say that triangle A dash R B dash is similar to triangle B dash P E dash. Hence we can say angle R A dash B dash is equal to angle P B dash A dash. These two angles are similar. If these two angles are similar, then angles made with normals are also similar. This angle is R A dash B dash can be written as 180 minus R, and P B dash A dash can be written as 180 minus I. So we can say that I is equals to R. So this proves the laws of reflection by using concept of wavefront. Now let us derive the laws of refraction using plane wavefront. First, let us state what are the laws of refraction. First statement says that for a given medium, the ratio of sine of angle of incidence to sine of angle of refraction is given by n, that is equal to sine I upon sine R. This is called Snell's law. And the second law states that incident ray, refracted ray, and normal to the surface at the point of incidence lie on same plane. And incident ray and refracted ray lie on opposite sides of normal. Let us prove this using the wavefront concept. Here we have taken two mediums, one is denser and one is rarer. Light rays are incident from a rarer medium to denser medium. As we know, if light ray travels from rarer to denser, it will move towards the normal. The first light ray will hit the surface and it will get refracted. At that time, the second light has reached up to this point only. So these 2 points are in phase. Now the time when second ray has hit the surface, the refracted ray has, this first ray has already entered in the denser medium. That means it has already refracted. So these 2 points are in phase again. Let's say V1 is the speed of light in rarer medium and V2 is speed of light in denser medium. Let's say incident ray is A dash B dash. So consider a wavefront of monochromatic light A dash B dash obliquely incident at a refracting surface. When the wavefront reaches point A, it becomes secondary wave in second medium. A dash B dash is equal to AB, which is equal to incident wavefront. When A dash reaches at point A, B dash reaches at point B. And B needs extra time t to reach x, y. Let's say distance traveled by light train medium 1 in this time is v1t. And distance traveled by light in medium 2 in same time is v2t. Here, speed of light in rarer medium is greater than speed of light in denser medium. So we can say V1 is greater than V2. So we can say V1t is greater than V2t. Considering V2t is less than V1t, with A as center, we draw a hemisphere of radius V2t. Now, during this time, secondary wavelets at A cover a distance V2t in denser medium. Now draw tangents CD to secondary wavefront. This CD is secondary wavefront. So CD is secondary wavefront. Now here angle A dash AN is equal to angle of incidence I. Angle CAM is angle of refraction R, and light NAM is normal to XY. This angle is 90 minus I. These two are perpendicular to each other. If this is angle of incidence I, then angle NAB will be 90 minus I. Now, we can say that angle MAC plus angle DAC is equal to 90 degree. So we can say that angle DAC plus angle ADC, angle DAC plus angle ADC is equal to 90 degree, as this angle is 90 degree. Angle MAC is equal to angle ADC is equal to angle of refraction R. From this two, we can conclude this. Now, let us take another triangle. Triangle BAD and triangle ACD. Let us take triangle BAD and triangle ACD. This angle is angle of incidence I, and this angle is angle of refraction R. In triangle BAD, we can write sine I is equal to, sine is opposite side upon hypotenuse, that will be BD upon AD. And in triangle ACD, we can write sine R is equals to AC upon AD. If we take the ratio, we can write sine I upon sine R is equal to BD by AD divided by AC by AD. This AD will get cancelled out. So we can write sine I upon sine R is equal to BD upon AC. But we know that BD is V1T and AC is V2T. So sine I upon sine R is equal to V1 by V2. Now, refractive index of medium 2 with respect to medium 1 is N2 by N1. N2 can be written as C upon V2 and N1 can be written as C upon V1. So V1 by V2 is equals to N21. Putting this value in this equation, we will get sine I upon sine R is equals to V1 by V2 is equals to N21. So here, Snell's law of refraction has been deduced from Eugene's wave theory. Now, incident ray, normal and refracted ray, they are lying on same plane. That is also correct. And incident ray A dash A and refracted ray A dash C are on the opposite side of normal. So that is also verified using this. Let us understand the Doppler effect using Eugene's principle. According to the Doppler effect, the apparent change in frequency of source due to relative motion between the source and the observer is called Doppler effect. Here we can see that the ambulance is approaching the observer. As ambulance approaches the observer, the frequency of the sound wave of the siren will change based on the relative motion between ambulance and the observer. Same thing can be observed for light also. So let us first note down what is the Doppler effect. It is the apparent change. Note the word apparent. The actual frequency does not change, but it is due to the relative motion between observer and listener, or observer and the source. We are feeling that change in frequency of source due to relative motion between the source and the observer is called Doppler's effect. It is not just only observed for sound waves, but also for electromagnetic waves, including microwaves, radio waves, and visible light. The detector or the source can be stationary or moving at given point of time. Let us consider a case where the observer is stationary and the source is moving towards observer. Similarly, we can also consider a case where the observer is stationary and source is moving away from the observer. Now, based on this, if source is moving towards the observer or away from the observer, the wavelength will change. Here in first figure, we can see that for approaching ambulance, apparent wavelength is lesser. So apparent wavelength has decreased. And for receding ambulance, the wavelength has increased. Same thing happens with light also, which is understood by the shifts. Let's say this is the observer. If the source keeps approaching the observer, then this would be the wavefronts. In this situation, the apparent wavelength will decrease if source approaches wavelength will decrease. So we can say that in the visible spectrum, the wavelength is shifting towards lesser wavelength. That means it is shifting towards blue light. In the VIBGYOR, 7 colors of visible light, violet, blue has least wavelength. So if wavelength is decreasing, we will call it blue shift. But for the same case, if this is observer and the siren is moving away or the source is moving away from us, then the wavelength will increase. Source is moving away here, so wavelength will increase. That means in the spectrum we are moving towards the right color, towards the red color. That's why it is called the red shift. So if wavelength decreases, it is called a blue shift, and if wavelength increases, it is called red shift. These concepts are used to find whether any star in the universe is moving towards the earth or it is moving away from the earth. Let us understand the Doppler effect in light. As light are the electromagnetic waves, there is no requirement of medium. So the Doppler effect in light is symmetric. The meaning of symmetric is that it depends only on the relative velocity of the source and observer measured relative to the medium. It only depends on relative motion or relative speeds of source and observer. It does not depend on medium property. The speed of light remains constant in given medium, whether light source is moving or not. For given medium. So the formula of frequency of light can be given by f dash is equals to f1 plus or minus VR by C. Or you can simplify this as C plus or minus VO divided by C plus or minus VS. Here VO is the velocity of observer and VS is velocity of source. Here we have to consider the sign convention. For sign convention, observer to source. This is observer and this is source. This direction is taken positive direction. So we can have different cases. We have to take O2 as direction as positive. Case 1, if observer is moving away from the source and source is stationary. In this situation, VO will be negative and VS is 0. So F dash will be equal to F into C minus VO divided by C. Second situation. Again, source is stationary and observer is moving towards the source. O2's direction is taken positive. So we can write F dash is equals to F into C plus VO divided by C. Same way, we can also consider this situation where source is moving towards or away from the observer. Just remember that always we will take O to S direction as positive. Here, we can, by using this formula, we can also find the apparent change in wavelength. As C is equals to F lambda or V is equals to F lambda dash. We can write 1 upon lambda dash is equals to 1 upon lambda 1 plus or minus VR upon C. Here VR is the velocity of source with respect to observer. So if we simplify and solve this, we will get delta lambda by lambda is equals to VR by C. This is the important formula for numerical purpose. What is redshift? If observer and light source move away from each other, then the apparent wavelength will increase. And shift towards red color. As wavelength increases, frequency will eventually decrease. What is blue shift? If the observer and light source move towards each other, then the apparent wavelength will decrease and shift towards blue color. That is called blue shift. And as wavelength is decreasing, frequency will increase. Now, what are the applications of Doppler effect? The first application is to find velocity of receding or approaching distance of stars or galaxies. To find the velocity of receding or approaching distance of stars or galaxies. We will observe the light rays coming from the planet or the stars. If its wavelength increases, then it is moving towards the earth. If it is shifting towards blue, then it is approaching. That means it is moving towards the earth. And if the wavelength received is moving, is shifting towards red color, its wavelength is increasing, then it is moving away from the earth. Same is the case for galaxy. The second effect is to measure the speed of rotation of the sun. Here we can see that due to rotation of sun, the wavelength of light received will keep changing. By finding the time period of this change, we can find the Doppler shift in kilometer per second. While rotating, one edge of the sun approaches the earth and other is moving away. The spectrum of both the edges matched with the spectrum of earth. Hence, we can find the rotation speed of sun, which is approximately 2 kilometers per second. The third application is to find the velocity of plasma particle vibrating at very high temperature. How we can find it? Let us see. We can use the concept delta lambda by lambda is equals to VR by C. Now, the RMS value is calculated as under root 3 RT by M. R is molar gas constant, T is absolute temperature, and M, capital M, is molar mass. Put the value here and we can find VR. This is all for today. Thank you.